Okay, so let's continue from where we stopped, and we defined some traces of the abstract data type Q, and also some sequences of operations which for different reasons did not belong to the set of traces of the abstract data type Q. So the thing to keep in mind again is that all these operations that we are generating as parts of these sequences, they are atomic operations. So for instance, if you enqueue a 5, then the operation will be performed atomically by the abstract data type. And if you dequeue a 3, then you send the request to the abstract data type and you get the answer as an atomic operation, etc. Finally, we define the abstract data type of a stack, and it's very similar to that of a queue. So the story is the same regardless of what you define. And as part of the first assignment, in fact, you'll be asked to define an abstract data type and then implement a simple program that satisfies the abstract data type, where satisfying is in a sense that I will define later today and on Wednesday. So a stack, again, as an abstract data type, it consists of 4 objects, as usual: set of states, initial state, set of method names, and the set of rules. So again, in the case of a stack, the state of the stack is a word of the set of integers in the same way as we had for queues. The only difference is in the operational semantics. So the methods are called push and pop for historical reasons, where push is like enqueue, add to the stack, and pop is like dequeue, remove from the stack. The set of rules, again, are defined by guarded commands. Again, we have a set of rules very similar to the set of rules in the case of queues. The only difference is that the push and the pop are both performed from the same end, which corresponds to the fact what we said in the previous lectures, that when we had a stack, we always work with the topmost element in the stack. So you see, now things are getting more concrete. So we'll define a stack as an abstract data type with an exact definition, or reasonably exact, given that we are not using formal methods as such, but reasonably exact definition. And then we will instantiate these definitions in the case of sequential programs and later concurrent programs. Anyway, the set of rules. If you have a word W corresponding to the content of the stack at the moment, then you can do push of A for some A, after which you concatenate A or append A to the end of W, where the end now is considered at the left part of W. You can do a pop A, which means that if A is at the head of the stack, then you can pop it. And as a result, you obtain a new word in which you have removed the A from the stack. So always when you pop, you remove the topmost element in the stack. And again, in a similar manner to the case of queues, if the stack is empty, then we do pop of some constant star, indicating that the stack is empty and we do not change the state of the stack. So it remains empty after this operation. And again, now we can define the set of traces given that the stack is initially empty. So the initial state is given by the word which is empty, epsilon, the empty word. So we start with an empty stack because we start with the initial state and we try to build a trace. So now we can push 3, which means that you add 3 as the topmost element in the stack. And because the stack is empty, so I just add 3 to the list. Now, if I do push 7, then according to this rule, I have to push 7 to the end of the stack, to the top of the stack, which is the left-hand side of the stack, which means that I just concatenate 7 with the 3. Now I can push 5, and this is similar to the previous cases. I add 5 as the topmost element of the stack. Now if I pop, then I pop 5, which means that I remove the 5 from the top of the stack. So again, if you compare with the case of queues, here the push operation has input A, no output. You can always push an element to the stack. And pop has no input, but an output A, which means that you don't give an argument, but you get back the topmost element of the stack, or what was the topmost element of the stack that has now been popped and removed. And this will become more concrete when you implement these data structures as programs. So we did the pop 5, which means that I remove the 5 from the top of the stack. And I can do pop 7, which means that I can remove the 7 from the top of the stack. Sorry. Now I have obtained a trace. So the set of traces of a stack is again defined by starting from the empty stack and then pushing and popping until the end with operations that are allowed according to the rules. Okay, any questions? No? Okay. So again, we emphasize that these operations are executed atomically. And the message to take from this part of the course is that traces are sequences of atomic operations which correspond to starting from some initial state and then performing a sequence of operations atomically, and in such a way obtaining a trace of the abstract data type. Okay, so now we go back to the outline of the course. So now we have done the overview, we have done the abstract data types, and now we start with sequential programs. These are programs that we already know from previous courses. So I suppose that everybody has at least written one sequential program. And sequential programs, we will go through different sub-items, if you wish. We look at programs, and now the programs will generate, so you can say that programs are refinements. We see them as refinements of abstract data types. So instead of traces, they generate histories, first sequential histories, because we deal with sequential programs. And the idea when history is that now, or the only difference compared to a trace is now the operations are not atomic. So in fact, each operation will be assumed to take time from invocation to getting response from the program. And this is not very important in the context of sequential programs, but nevertheless, we do view the operations as not atomic, because then it will be much easier to generalize the concepts to the case of concurrent programs, where we do need to view operations as non-atomic. So again, we define notional programs, define sequential histories. These are, if you wish, the traces that are defined by the programs. And in fact, we define a mapping which take each history and transform it into a trace by simply collapsing the invocation and the response of an operation and making them into an operation, and in such a way obtaining a trace, as we will see later. So this means that we will define the notion of traces of a program. The traces we get by looking at the histories that are generated by the program and transforming each history into a trace. And we will make things more concrete by looking at an example of a sequential program that implements a set. It's a simple program as a linked list, it's implemented as a linked list. And therefore we obtain a transformation from programs to histories to traces. So as I told you in the first lecture, we will work with different hierarchy of different abstraction levels. So the most concrete one was that of a trace, in which operations were atomic. The next level of abstraction is sequential histories, in which operations are not atomic, but they are sequential in the sense that each invocation of an operation is followed immediately by a response from the program. And this reflects the fact that in a sequential program, it does interact with the system, but when it issues an operation, when it interacts with the memory, for instance, it waits for the memory to answer before it proceeds to the next instruction. And this will be more concrete after we have gone through the details of our models in this part of the course. So we start with programs. So what's a program? Well, for me, at the moment, the program is just a black box. And this black box, it performs a number of operations. So in this course, we will be interested in a particular class of programs, namely those that manipulate basic data structures. So this means that inside the program, you will have some data structures that implement a given abstract data type with which the user can interact. So recall that from the abstract data types, operations were atomic. Now, the difference in the case of programs is that the operations that we perform, they are not performed atomically. This will be the main difference. And this is what it means to go one level up in the hierarchy of abstractions that I was talking about vaguely in the previous two lectures, but now it will be more concrete. So you have non-atomic operations that are performed by the program. And the idea or the intuition behind this is that an operation in reality takes time from the point at which you issue the operation to the point at which the operation has fully taken effect. So, in fact, we can view operations as consisting of two events, invocation and response. So an operation is, rather than being atomic, it is now refined into two operations, an invocation and a response. So we can say that the program is a refinement of an abstract data type in the sense that its operations are non-atomic, and correspondingly, a history that, as we will see, is a refinement of the notion of a trace, again, in the sense that the operations in the case of a history, these operations are not atomic. So this means the following. If you have a program, then if you perform an operation, then you invoke. And when you invoke an operation, you give it the operation name and the input. Remember, an operation consisted of three parts: a name of the operation, an input, and an output. So now when you implement such an operation or an abstract data type as a program, you interact with the program through some invocation of invocation events in which you, as we will see, you will give the operation name as well as the input. And as an output, you get a response. So the program responds to the invocation and produces some output. So let's try to instantiate this to the case of sets. So there, for instance, if I want to perform an operation add 3 and true, for instance, so this will not be performed atomically. First, I provide the operation name, which is add, and the 3, which is the input. This is the invocation. After some time, the program, this is the name of the operation, and this is the input value. So after some amount of time, you get a response, which is the output value, which is true in this case, because this program is implementing a set somehow, and we have still not defined how it does that. For instance, as a linked list. So when you add, you issue the operation add 3. This is given to the program. The program will take some time. It manipulates its input state, which is a list, maybe in this case. And then after some time, it reports to the user, to the program that has issued the operation that it was successful. So presumably because C was not there, and the program added it to the list of elements that are available. Okay, so sequential histories. Let's look at that. What does it mean? So again, a sequential history is like a trace, but just that the operations are not performed atomically. So we do add 3, invoke an operation, name, input value, And then at the time axis, we record the name and the input, and we call this the invocation. And then after some time, you get the value, the output value, which is true from the program, and then we record. This is the output value, and we record this output value. And now this is, so now you have the invocation, and then you have the corresponding response. So you see here I have drawn these arrows, which means that this response corresponds to this invocation. And so you have the invocation and the response. And this is the call. So what's a call? It's the interval between the invocation and the response when performing an operation. So a method call is if you wish, a non-atomic execution of an operation in which you first provide, you have the invocation where you provide the method name and the input value. As an output, you get the output value here, which is true. And the interval in time between these two events is called the call. Now, the thing is that with sequential programs, it's always the case that the invocation is followed by a response. There is nothing happening in between because there is only one process by assumption. And this process will not initiate a new operation before it has made sure that this operation has correctly been dealt with by the program. In the concurrent setting, this will be quite different because some other thread may come here and perform some operations. So these calls will overlap. Not the case up to now. So now the interval between invocation and response is the call. Now maybe the program or the program issues another operation at 5. So this is the invocation and then response true. And these two things are together. So this one is the matching event of this one. The response here is the matching of the invocation here. So you see that here in the case of traces, we would get at 3 true in one atomic step, at 5 true in one atomic step. Here we have separated the invocation from the response. And in that sense, the operation is not atomic. And maybe we can do contain for, invoke, contain for, and then get a result maybe false. So presumably this program has started with a state where the set was empty, and now it has performed all these operations successfully. And at this moment, it knows that it has a 3 and a 5 inside the set, and therefore, if it gets a request or an invocation of contain for, it answers false. Remove 2. False. It cannot remove 2 because it has not added 2 to the set yet. Again, a new call. So now, in such a way, we have obtained the history, H. So remember, in the case of a trace, we defined the trace to be the result of starting from the initial state of the system, the initial configuration, and then performing a sequence of operations. And then collecting these the operations in one sequence, which you call the trace. Here we do the same thing. We run the program, maybe starting from some initial state, and then we look at the calls that we have made, and we collect the sequence of calls, and we call it a history of the program, H. So this is an example of a history. So a history then is a sequence of invocations and returns and responses. So any question up to now? Okay. And now at this stage, we assume that our histories are sequential. And sequential means that each method call is followed by a response. So in that sense, method calls do not overlap. So you see that all these calls, they do not overlap. One of them should end before the next one starts. all the time. And in such a history where we have a sequence of method calls, but in which the calls do not overlap, such a history is called a sequential history. So this is important, method calls do not overlap, which means that each invocation is followed immediately by the matching response. And in such a way, we obtain a sequential history. So now we have this abstract model of a program. What we did is that we viewed the program as a black box. We have still not opened the box and looked inside, which we will do soon. The only thing I know is that I can interact with the program by issuing calls, which you call operation invocations, and then I get returns in between. And this interval I call a call. And by taking a sequence of calls, I have a history H, and this history is sequential if the method calls do not overlap. So this is what I want you to understand up to now. If you have any questions, you are very welcome to ask. Okay, so now we transform this sequential history into a trace. And what we do simply is that we take each method call and we collapse it into an operation as expected by just merging the invocation with the response, obtaining an operation. So now we define the trace of H. So this is my H, this is my history. Now I collapse it into a trace, which I call the trace of H. So if I have obtained the history H, I can derive the trace of H as follows. Merge each invocation with the corresponding response. So let's do that. Take the first invocation and merge it with the response. And so this is the call, remember? And I transform it into an operation. So you see that by merging the call and the response of the call, I got an operation. So there is already a nice correspondence between the histories and traces, or between calls and operations, which translates into a relation between histories and traces. So what I'm doing is that I collapse a call into an operation in the obvious manner by taking the name and the input and the output and put them together. And this is exactly the definition of an operation. Remember that an operation was defined by its name, input, and output. And then we repeat the procedure for the other calls. Add 5 true, give me the operation at 5 true here. Contain 4 false, contain 4 false, remove 2 false, remove 2 false. You see here that I obtained a trace suddenly from the history. And this is very nice. It's simple, but it's nice because it will allow us to define a general picture when we get to the concurrent setting, where the methods will overlap. And now the non-trivial task will be to make all the what we call concurrent histories later, to make them sequential again so that we obtain the traces. And once we have obtained the traces, we can check whether they belong to the reference abstract data type. Anyway, at the moment, the only thing you need to know is that we know how to obtain define a history, we know how to derive a trace from a history. And now I have obtained a trace, tau, and I say tau is the trace of H, meaning that I obtained tau from H by collapsing its calls into operations. And the unique trace I obtain in this manner is the trace of H. So again, each history implicitly gives you a unique trace, namely the trace you get by collapsing the calls into operations. So this is important. What does it mean to have the trace of H? It's the trace I get by collapsing its calls into operations. So now, once I have done this, I can define the set of traces of a program. First, I define the set of histories of an abstract data type. So suppose that I'm given an abstract data type, A. And this can be a set, it can be a queue, it can be a stack. Any abstract data type. It can be a multi-set, it can be a priority queue. we define the set of histories of A, of this abstract data type, by saying that H, a history, belongs to the set of histories of A if the trace of H is a set in the set of traces of A. What does that mean? Well, it means that if you give me a history H, I define its trace by applying this operation. I take H, I collapse it to a trace by collapsing its calls into operations. Then I look at the trace. Does it belong to the traces of A, of this abstract data type? And we know what this means. If yes, then I say this H belongs to the set of histories of the abstract data type. So in that sense, an abstract data type not only defines a set of traces, but also it characterizes a set of histories, namely all the histories whose traces are traces of that abstract data type. So for instance, here, the tau here belong to the set of traces of set. If you look at this trace here, we know that this is a trace of the abstract data type set. Furthermore, we know that this history H is related to tau by the fact that tau is the trace of H. So on the one hand, this tau here is the trace of this history because I collapse this history to this trace. On the other hand, this trace is a trace of the abstract data type set. So these two things together will give me the fact that H here is in the set of histories of the set. Sorry. See here. So these two things gives me the fact that H is a history of the abstract data type set. So again, first, an abstract data type characterizes a set of traces. A history can be collapsed into a trace. If you give me a history, I can collapse it to a trace, and then I can see whether it belongs to the abstract data type. If yes, then that history also belongs to that abstract data type. If no, then that history does not belong to that abstract data type. Any questions up to now? If not, let's look at some examples. So the history H1, for instance, it's in the set of histories of a set. Why? Because if I collapse this history into a trace, then I obtain add 3 true, add 5 true, contain 4 false, remove 2 false. And this trace is a trace of the abstract data type set. Because here I'm adding 3, I'm adding 5, I'm asking for the containment of 4, which is false. And then I am trying to remove 2, which should be false because 2 has not been added. So this history is indeed in the set of histories of the abstract data type set. How about this history here, H2? What do you think? You can think for 10 seconds and see whether you think it should belong to the set of histories of set. So I'm adding 3 successfully. I'm failing to add 3. I'm failing to find 4, and I have succeeded in finding 3. In fact, yes, this is fine. It's a behavior of a set because the corresponding trace, which I get by collapsing the history into a trace, indeed belongs to the set of traces of a set. And therefore, the history H2 belongs to the set of histories of a set. How about H3? Add 3 successfully, fail to add 3, fail to find 4, and fail to find 3. So you see here, this is a behavior which is not consistent with the operational semantics of a set, because I have added 3, I have not removed 3, but I do not find 3 in the set. So if a program gives you such a history, then it violates, if you wish, the safety property, which tells you that this program should observe the abstract data type set. This we will make more concrete later, but at this moment, you already see the correspondence between concrete programs in our setting and abstract data types and safety properties that are defined in terms of abstract data types. So at least conceptually, we know now why H3 should not be a history of set, because its corresponding trace does not belong to a set. So how about H4? is it in the set of histories of a Q? So you see here, this is interesting because if you look at the method calls, you see that this is the operation name. This is the input. There is no output. So I just put a dot here. So this corresponds to the operation that you first requested in Q3. After some time, the program told you that it has done it, but it does not give any output. And then in Q5, and then for the DQ, it's the other way around. You invoke the operation by just giving the method name because you don't have any input. After some point, you get the output, which is the value 3. And then the same thing here. You have DQ operation without input, and you get the value 5. And indeed, this is a history. H4 is a history of the abstract data type Q, because you in Q3, you in Q5, DQ3, DQ5, which is fine, consistent with the operational semantics of a Q. H5 is not, because here I'm enqueuing 3, enqueuing 5, dequeuing 5, which is not consistent, so I'm dequeuing in the other way round, or the other order. So this is, in fact, this history belongs to the history, set of histories of a stack, but not the set of histories of a queue. So this is all what we have with histories. So they are refinements of traces. We get them by collapsing traces, and we collapse a trace by collapsing we get a trace, we collapse a history by collapsing its calls, obtaining operations, and in such a manner we obtain the traces. And then we check whether the trace corresponds to the set or is a member of the set of traces of the given abstract data type. So any questions? Okay, I'm getting a bit tired. Let me see. Okay. So now what we have done program sequential histories, from histories to traces. Let's look at an example of implementing a set. So again, let's go back to our model of a program as a black box with an interface which corresponds to invocations and responses to different operations. And this allows me to define a trace in 2 steps. First, I define history, which I transform to a trace. Now, let's look at inside the program. So how would I implement such a program? And this is what you will be doing in the first lab, in fact. Well, as I told you, we consider a special class of programs in this course, namely those that implement abstract data types. So they are special in the sense that they perform, what they do is that they perform different operations that correspond to the set of methods of that abstract data type. So this means that typically inside the program, you'll have 3 modules that implement the 3, for a set, or you have a set of modules, each of which corresponds to an implementation of the corresponding method. So let's take a program P that implements a set, and let's define the set of histories of P. So now, when we implement the program P, we get a set of histories. These are the histories that we get simply by running the program as I described. And this, as we said, this will allow us to define the set of traces of P by taking these histories and collapsing them into traces. So the set of traces of P is the traces I get by taking the histories of P and then apply this operation trace off to the histories of P, obtaining the set of traces of P. And now I can compare the set of traces of P with the set of traces of the abstract data type. And this we will formulate as a safety property. So this I will explain more later. But if you look inside the program, so this is what we will do now. So again, let me try to repeat this. It was a bit quick. So if you look at the full picture here, we are given an abstract data type defined by a set of traces. Now we are trying to implement a program that satisfies the abstract data type, program P. This program will generate for me a set of histories. Now, these histories I can call up to traces. And this I call the traces of P. And I have to make sure that the program P generates a set of traces, each of which belongs to the set of traces of the given abstract data type. For instance, a set in this case. So this means that I look inside the program and I find three modules. These are three subroutines in the program, each of which implementing one of the operations. Because I have a set, so I have add k, remove k, contain k. And as a black box, the program takes as input invocations of these operations. And now these modules, depending on which input you give to invoke, which operation you give to invoke to carry out, one of these modules will be activated. And after a while, it produces a result which will send out to the caller. So, and how this is done is that typically you'll have a common data structure that's shared by these operations, by these modules. If you look inside the data structure, they correspond to the state, the current state of the abstract data type. So in the case of a set, this is a data structure that stores the elements inside the set. How you do that is up to you. It can be a tree, it can be a doubly linked list, it can be a linked list, singly linked list. In these lectures, we will start by singly linked lists. So what will happen is that these modules will interact with the data structure. So if you invoke, for instance, if you do add3, so you remember an invocation is a method name together with some input value. So if you invoke by add3, now because the method name is add, it is the add module that will be activated. So this means that what the program does is that it takes this add3 and it puts the 3 as input to the add k module, where k is the input parameter. So the input value is k, in this case it's 3. Now what the add module does is that it interacts with the data structure. So it invokes an operation. So you see the invoke at the external level is internally translated into an invoke at the internal level. And this, what I want you to implement in the lab in a way that will be more explained, of course, on Friday. And this invocation will be sent to the data structure. Now, what the add module does is that it looks inside the data structure and it asks whether 3 is already there or not. So if not, then it will add it to the data structure. So it asks, is 3 there or not? And the data structure, what it does two things. It changes its state. For instance, if add is successful, it will add 3 to its state. So it obtains a new state. This corresponds to changing the state of the abstract data type. So the state changed from yellow to orange. And it answers true in this case to the add module. And now this is the response that the add module will provide to the program like this, and this will be propagated to the caller. So what will happen is a bit complicated, and it's important that we do it like that because this is the only way to do it when you have concurrency, in fact. So we invoke the operation in add3. This activates the add module with the value 3 to k. The add module asks the data structure about 3. If not there, the data structure changes state and answers true, which means that true, I have successfully added the 3. And now I return the value true, and this will be in turn returned to the caller. So the important thing here is that this will be done, perform two operations: change state return value, and propagate the value outside. And this is why operations are not performed atomically at the program level. So you see here that we have a lot of operations, but at the abstraction level, when you view the whole program as a black box, you see an invocation and a response. And in fact, if you collapse these two guys here, then you obtain an operation. So this is the general model that you will use throughout the course. The only difference will be that in the case of sequential programs, you will have one process that interacts with this implementation of the program, while in the case of concurrent programs, you will have multiple threads that operate in parallel and their operations may overlap. So I think I will stop here for if there are any questions, I can answer questions. And again, as I told you, if you want to ask questions later, you can mail me questions. That is fine also. So what we have done up to now is that now we have moved up in the hierarchy of abstractions. We started, of course, we started very informally by notions like specifications. Now we got more concrete by abstract data types. And then now we are dealing with, we used abstract data types to define traces. And now we are dealing with concrete programs, which in this manner generate method calls as invocations and responses, which we collapse to operations, and in such a way we translate the history generated by the program into a trace generated by the program, and later we will compare this trace with the one of the expected data type, for instance, of a set, to see that all the traces generated by the program are indeed traces that satisfy the abstract data type. And in such a case, we say that we satisfy the safety property. So let me see, there is one question. Is the ask operation atomic? Well, no, it takes some time, of course, to answer. So the whole thing is non-atomic. I mean, of course, everything when you say atomic, non-atomic, these are like modeling issues. So at what you see as atomic or non-atomic. This will be more clear when we deal with concurrency, but I don't see it as atomic, because it takes some time for this data structure or to check the data structure and to change its value. So the non-atomicity comes from different parts to manipulate the data structure and to take the input values and to propagate out the output values through the system. So is it clear? Carry on. Okay, any other questions? Thank you. So otherwise, we stop here in the next lecture, which is on Wednesday. And now for people who are not registered at Student Portal, and I have added a copy of the schedule to this temporary directory, to this temporary link. So it will be on Wednesday, where I continue with sequential programs, histories, and then if I have time, I will start with concurrent programs and start to define the notion of linearizability. So thank you very much and see you then. Bye.